Welcome to another edition of Math for No Reason. In this edition, we look at this problem. Let A be a n cross n matrix, and we define exponential of A as summation of k equal to 0 to infinity 1 by k factorial a to the power k. Now, the problem asks us to find the determinant of this matrix exponential A. Now, to do this, we will use the eigenvalues of the matrix A. Recall that lambda is an eigenvalue of A if Ax is equal to lambda x for some x not equal to the 0 vector. So these n's are n cross 1 vector. So this is a n cross 1 vector. Lambda can be real or complex number. And if we have this condition met, then we say that lambda is an eigenvalue. So let lambda 1, lambda 2, lambda n be the eigenvalues of A. Then we know that the determinant of A is the product of the eigenvalues of A. So we will use this result to find out the determinant of exponential A. Now, we will first try to find out the eigenvalues of exponential A. So, what are the eigenvalues of exponential A? Let x1 be the eigenvector corresponding to the eigenvalue lambda 1. Now, if we are looking at exponential A into x1 tilde, we have summation k equal to 0 to infinity 1 by k factorial a power k into x1. Now, multiplying term by term, assuming all the convergence conditions are met, which are met in this case, though I am not proving it here, we have 1 by k factorial ak into x1. We consider ak x1 and write this as a k minus 1 into a x1, and since x1 is the eigenvector corresponding to the eigenvalue lambda 1, this is a k minus 1 lambda 1 x1. So we can write this as lambda 1 a k minus 1 x1. Now this is again can be written as a lambda 1 a k minus 2 into a x1. Again, using a x1 is lambda 1 x1, we can write this as lambda 1 square a k minus 2 x1, and we can repeat this argument several times to get this as lambda 1 power k x1. So, what this result tells us is that if lambda 1 is an eigenvalue of A, then lambda 1 power k is an eigenvalue of A power k, and this is going to be very useful. So, in the proof that we discussed, lambda 1 could have been replaced by lambda 2 or lambda 3, and we would have got the same result. Thus, we claim that if lambda is an eigenvalue of A, then lambda power k is an eigenvalue of ak. And thus, when we are looking at exponential A into x, where x is the eigenvector corresponding to the eigenvalue lambda, then we have, and this a power k lambda x, we can replace it by lambda power k x, and this we can write as, and this is nothing but e to the power lambda. So we have, this is e to the power lambda x. So what we have is exponential of ax is e to the power lambda x. So if lambda is an eigenvalue of a, e to the power lambda is an eigenvalue of exponential A. So if lambda 1, lambda 2, lambda n are the eigenvalues of A, then e to the power lambda 1, e to the power lambda 2, e to the power lambda n would be the eigenvalues of exponential A. Okay, so that is a key result which I write down here. Now, once we have the eigenvalues of exponential A, obtaining the determinant is straightforward because the determinant of the exponential of A is nothing but the product of the eigenvalues, which is e to the power lambda 1 into e to the power lambda 2, etc., e to the power lambda n. And this is nothing but e to the power lambda 1 plus lambda 2 plus lambda n. Now, the sum of the eigenvalues is called the trace. So, what we have got here is e to the power the trace of A. So, the sum of the eigenvalues is called the trace of a matrix A, and that is denoted as TR of A. So, what we have proved? We have proved that the determinant of exponential A is actually equal to the exponential of the trace of the matrix A, and that is a key result that we have proved today. Thank you.